The bone probe breaks silence, a Central Inuit engineering secret forgotten by modern science. 90 seconds decide everything. Will this snow hold a home warmer than yours? A Kalaalleq builder's forgotten knowledge still outlasts the calculations of today's engineers. At -40°C, this 2-hour structure will outperform the insulated wall of a modern American home. Inuit engineers of Nunavut solved that physics approximately 4,000 years before building science existed as a field. The word igloo comes from the Inuktitut word igloo, meaning simply house. It is not a generic Arctic shelter. It is not a universal cold weather solution. The domed snowblock construction belongs specifically to Central Inuit peoples, the Igloolik, Kivalliq, and Kitikmeot communities of what is now Nunavut, Canada. That distinction matters. This is not a pan-Arctic technique borrowed loosely from neighboring cultures. Yupik peoples, Inupiat peoples, and Siberian Arctic communities developed their own distinct cold weather shelter systems. The igloo is a Central Inuit engineering solution specific, refined, and documented. The technology is documented in continuous use from at least 4,000 years ago, when ancestral Thule culture predecessors built snow shelters across Arctic northern Canada and Alaska. By the year 1000, Thule culture direct ancestors of modern Inuit had carried igloo construction knowledge across approximately 6,000 miles of Arctic coastline. That is the distance from New York to London, then to Moscow, covered by a single standardized building technology. In 1824, British Royal Navy Captain George Francis Lyon documented igloo wall thickness, dome geometry, and interior temperature differentials during an Arctic expedition. He was not discovering anything. He was writing down what Inuit builders had already solved. In 1960, Canadian National Research Council engineers published thermal conductivity studies of snow as a building material. They confirmed what Inuit engineers had applied empirically for millennia. Snow insulates at approximately 0.1 to 0.16 watts per meter Kelvin, depending on crystal density. That is the modern scientific framework, arriving roughly 4,000 years after the engineering practice. Today, we are going to measure what that practice achieves in watts, R values, load-bearing capacity, and thermal differentials. We are going to put a thermal camera on a completed igloo at -30°C, and then we are going to point that same camera at a modern wood frame house standing next to it. The result will ask you to reconsider which structure is more sophisticated. The field documentation that follows is drawn from Nunavut, Canada, year 2003. The snow is wind-packed. The temperature at the surface is -28°C. The builder is reading the field before a single block is cut. That reading process is where we start. The tool in the builder's hand is a Kazaka snow probe, made traditionally from bone or antler. It is driven into the snowfield with short, vertical strokes, 6 to 8 inches deep. The builder is not guessing. He is performing a material science assessment. Inuit builders distinguish a minimum of 10 functionally distinct snow types by texture, compressive resistance, and sound. That classification system is documented in the 2010 publication, Siku, Knowing Our Ice, edited by Igor Krupnik and colleagues, published by Springer. 10 categories, no instruments, assessments, completed in under 2 minutes. Think about the metaphor here. This is like selecting the right grade of lumber at a hardware store, except the builder is reading grain, density, and load-bearing capacity in a material that looks identical to the untrained eye. And he is doing it in under 2 minutes with a stick. What he is looking for is wind-packed snow crystals that have been mechanically interlocked by wind compression over days or weeks. The crystal interlocking creates structural cohesion. This is the same principle as sintered metal or pressed powder ceramics. A hollow thud under the probe means the crystals are loose, granular, insufficiently bonded, wrong density for structural blocks. A firm resistance means wind-packed interlocking construction grade. The entire structure will stand or fail based on this 90-second assessment. 90 seconds. The whole load calculation is in that sound. Now the cutting begins. The snow knife, traditionally made from bone, ivory, or later metal, scores the surface in long, controlled strokes. The blocks that come out are approximately 60 centimeters long, 40 centimeters wide, and 20 centimeters thick. Each block weighs between 15 and 30 kilograms, depending on crystal density. The builder cuts in a spiral pattern, not a series of flat courses stacked like bricks. This is the engineering decision that makes everything else possible. By cutting the base in a ramp, each course of blocks tilts slightly inward toward the center as it rises. The structure is not stacked, it is curved, continuously, toward a single closing point at the top. This geometry is called a catenary dome, a self-supporting arch formed by the natural curve of a hanging chain, inverted. A catenary distributes compressive load across the entire structure, with no internal supports required. Every block in the dome is in compression, pushing against its neighbors, not pulling away from them. Remove any single block from a completed igloo, and the structure will begin to shift. But under normal conditions, the compression locks everything in place. A completed igloo can support a standing adult, approximately 180 to 200 pounds on its exterior roof, without structural failure. That is documented in U.S. Army Cold Regions Research and Engineering Laboratory technical reports, published by CRREL in Hanover, New Hampshire. This is not a fragile snow fort. This is a load-bearing compression arch. The construction time for a single-occupancy igloo, 1 to 2 hours. A family igloo of 10 to 12 feet interior diameter, 2 to 3 hours. Faster than assembling most flat-pack furniture, completed before a feature film ends. 2 hours. From open snowfield to standing structure. Those are not estimates. They are documented construction times, recorded in multiple Arctic ethnographic records, including Franz Boas's 1897 documentation of Central Inuit construction. But the speed is not the revelation. The thermal performance is. The wall thickness of a standard igloo is 30 to 40 centimeters, roughly the width of 2 standard hardcover books stacked side by side. At that thickness, using construction-grade snow at 0.16 watts per meter Kelvin, the wall achieves an estimated R value of approximately 3.5 per inch. Modern fiberglass bat insulation, the pink material stuffed into the wall cavities of new American homes, is rated R3.1 to R4.3 per inch. The igloo wall and the fiberglass bat are performing at the same per-inch insulation level. The igloo uses 0 manufactured materials, 0 factory inputs, 0 external energy for fabrication. The fiberglass bat requires a 3.5-inch minimum wall cavity, a wood frame structure, before it can be installed. The igloo wall is monolithic, self-supporting, and load-bearing, with an equivalent insulation value, built in 2 hours from the ground it stands on. That comparison comes directly from U.S. Department of Energy insulation R-value specifications, cross-referenced with Arctic engineering literature from CRREL. But the wall thickness is only part of the thermal system. The geometry of what is inside the wall is the other half. And here is where the engineering goes from impressive to precise. Inside the igloo, air does not mix evenly. It stratifies. Warm air rises, cold air falls. This is basic thermodynamics. The igloo's interior is engineered around it. The sleeping platform is raised above the entrance tunnel floor by a deliberate step, typically 30 to 60 centimeters. That elevation positions the occupant in the warmest air layer inside the dome. Interior temperature at the sleeping platform level, approximately 15 to 16 degrees Celsius, 59 to 61 degrees Fahrenheit. Exterior temperature, negative 40 Celsius. That is a differential of 56 degrees Celsius, the temperature difference between a comfortable living room and the surface of dry ice. Achieved with snow walls, a raised platform, and body heat. The cold air, meanwhile, does not stay inside. It drains. The entrance tunnel is deliberately dug below the igloo floor level, creating a physical cold air trap. Dense cold air flows down and out through the tunnel. Warm air stays in the dome above. This is passive HVAC. There are no ducts, no fans, no thermostat. Please. The geometry itself manages airflow. The heat source inside that geometry is a quillic, a shallow oil lamp burning seal or whale oil. Heat output of a quillic, approximately 60 to 100 watts. That is roughly the heat output of a single incandescent light bulb. 1 incandescent bulb's worth of heat, inside snow walls, is sufficient to maintain interior temperatures above freezing when the outside reads -40°C. That performance figure is cited in Smithsonian Arctic Studies Center documentation and multiple ethnographic records of Quillic use. A modern single-room electric space heater outputs 1,500 watts, 15 times more power, and still loses heat through the walls of a conventional insulated room. The igloo does not lose heat through its walls the way a modern house does. The snow absorbs and re-radiates heat, buffering the interior against the temperature swing outside. Snow, as a thermal mass buffer, not just an insulator. The wall is doing two jobs simultaneously, blocking conductive heat loss and storing thermal energy in the crystalline matrix. And there is a third job the wall is doing that no modern insulation material does at all. The snow breathes. Unlike a sealed modern room, the igloo's snow walls are slightly porous, allowing slow, passive gas exchange between the interior and the exterior. This prevents dangerous carbon dioxide buildup from occupant respiration and from the Quillic flame. No vents, no fans, no mechanical ventilation system. The microporosity of the snow crystal matrix maintains safe air composition passively. Inuit builders also cut a small ventilation hole near the dome apex, using a stick, calibrating airflow by adjusting the stick's diameter in the opening. Variable aperture passive ventilation, that is, HVAC engineering, solved approximately 4,000 years before the invention of ductwork. So the structure is standing, the physics of the wall are confirmed, the air stratification is engineered, the ventilation is passive and calibrated. Now the question becomes, what does all of this look like on a thermal camera? Because the most counterintuitive result of this engineering is not a number on a datasheet. It is what the infrared image shows when you point a thermal camera at both buildings on the same night. The thermal camera is set up at 200 meters from the completed igloo. Exterior temperature, -30°C. Wind, approximately 15 kilometers per hour. Clear sky. Wind. The camera reads thermal radiation heat escaping from surfaces. Hot objects glow orange and yellow. Cold surfaces stay dark blue. The igloo appears on the screen. The igloo is nearly invisible to infrared. The snow walls are absorbing the interior heat so efficiently that almost none of it reaches the outer surface. There is one small orange signature, the ventilation hole at the dome apex, where calibrated air exchange is occurring by design. One deliberate warm spot. Every other surface is cold. A building generating 16 degrees Celsius inside, invisible to heat detection equipment outside. Now the camera pans left. The modern wood frame house beside its standard construction, vapor barrier, R13 fiberglass bat wall insulation, double-pane windows appears on screen. It is blazing, orange along every window frame, yellow across the roof deck, bright orange at the foundation sill. The wall surfaces themselves show elevated temperatures compared to the surrounding snow-orange tinted heat radiating outward continuously. The igloo is losing almost no energy to the environment. The modern house is broadcasting its thermal energy into the Arctic night from every surface. This is the moment the comparison becomes structural, not rhetorical. The igloo does not outperform the modern house in absolute interior comfort. A modern house can reach 22 degrees Celsius. The igloo outperforms the modern house in thermal efficiency, energy retained per unit of heat generated. With one lamp and body heat totaling perhaps 200 watts of input, the igloo holds a 56-degree differential. A modern house with a full forced air heating system running at thousands of watts bleeds that energy continuously through its walls, windows, and roof. The thermal camera is not showing us which building is more comfortable. It is showing us which building is more engineered. Now we go back to the snow probe. Because none of this thermal performance happens without the material selection that precedes construction. The thermal conductivity of snow is not fixed. It is a variable controlled by crystal density. Freshly fallen snow, approximately 0.1 watts per meter Kelvin, very low density, crystals loosely arranged. Wind-packed construction snow, approximately 0.16 watts per meter Kelvin, higher density, crystals mechanically interlocked. Solid ice, 2.33 watts per meter Kelvin. Construction-grade snow is approximately 15 times more insulative than solid ice, built from the same water molecule in a different crystal arrangement. The Canadian National Research Council confirmed these values in 1960. The figure 0.16 watts per meter Kelvin appears in their building materials research for Arctic construction. The Inuit builder, selecting snow by sound and resistance in the field, is making a thermal conductivity assessment without a conductivity meter. He is sorting materials by the same physical property a laboratory instrument would measure through calibrated sensory feedback developed over generations. This is not intuition. Intuition is undefined. This is applied materials science performed without instruments. The instrument is the probe. The readout is the sound. Zacharias Kunuk, Inuit filmmaker and founder of Isuma Productions in Igloolik, Nunavut, has described this knowledge directly in recorded interviews. He said, in paraphrase, "We have many words for snow, because snow is not one thing. The snow that holds your weight is not the snow that fell last night. You have to know which one you are standing on." That statement is not poetic. It is a precise description of material property differentiation, the same distinction a structural engineer makes between load-bearing and non-load-bearing members. The builder is standing on the material selection floor of his construction site. And here is where the evidence gets harder to ignore: the moment the dome closes. The dome is rising. The spiral of blocks has completed its second full course, tilting inward by approximately 5 degrees per course. Each block is cut to a slight wedge shape, wider on the outside face, narrower on the inside, allowing it to tilt inward and lock against its neighbors under gravity. The catenary geometry means the structure is self-bracing before the final block is placed. As the dome closes, the interior becomes increasingly confined. By the final course, there is room for one person inside. That one person is the builder. The final block, called the keystone, must be cut from inside the structure by the builder, who is now enclosed within a nearly complete sphere of snow. The keystone is cut slightly larger than the opening it will fill. It is tilted at an angle, inserted diagonally through the gap, then rotated into horizontal position and pressed upward into the hole from below. The block is larger than the opening. It cannot fall through. It locks against the surrounding course in compression. This is a three-dimensional puzzle piece inserted by someone standing inside the puzzle. If the geometry calculation was off at any earlier course, if any block was cut at the wrong angle, if any course tilted too steeply or too shallowly, the keystone will not fit, or the dome will shift as it is placed. This moment is the final structural test of every measurement decision made in the preceding 2 hours. It almost never fails. When the keystone locks, the structure becomes self-supporting in approximately the time it takes to remove your hands. The builder then uses snow from inside the structure to chink gaps between blocks, a mortar layer that freezes into place and increases thermal sealing. The entrance tunnel is excavated next, dug below the interior floor level, angled downward and then upward to exit at the surface. The downward dip is the cold air trap. Warm air cannot flow down and out. Cold air cannot flow up and in. The tunnel functions as a heat lock, the same principle as an airlock on a spacecraft, preventing thermal environments from equalizing. The sleeping platform is packed hard inside, raised above the tunnel exit level. A small hole is made at the dome apex with a stick. The stick diameter controls the ventilation rate. Larger stick diameter, more airflow, lower interior humidity, lower CO2 concentration, smaller diameter, less heat loss, higher warmth retention. Variable passive ventilation, adjustable by the occupant, requiring 0 mechanical components. Some igloo builders cut a small window into the dome wall, a thin piece of freshwater ice, scraped to translucency, or a panel of scraped seal intestine stretched across a frame. Both materials transmit daylight while maintaining thermal integrity in the wall. Translucent structural glazing integrated into a building envelope that is the functional description of a modern polycarbonate skylight. Polycarbonate glazing was developed by Western architecture in the 20th century. Inuit builders were installing translucent envelope glazing thousands of years earlier, using available Arctic materials. The Smithsonian Arctic Study Center documents this material use in Arctic architectural records. Every feature of the igloo is an engineered response to a specific physical problem. Thermal conductivity of walls, addressed by snow crystal selection. Structural load distribution, addressed by catenary dome geometry. Interior air temperature stratification, addressed by raised sleeping platform. Cold air infiltration, addressed by sunken entrance tunnel. Ventilation and CO2 management, addressed by porous wall microstructure plus calibrated apex vent. Daylighting without thermal compromise, addressed by translucent ice or intestine glazing. This is not a list of survival hacks. This is a complete passive house performance specification. The phrase passive house refers to a specific category in modern sustainable architecture, a building that maintains comfortable interior temperatures with minimal active heating through insulation, air sealing, and solar gain. The Passive House Institute, based in Darmstadt, Germany, developed its first certification standard in 1991. The Igloo has been meeting equivalent performance criteria for approximately 4,000 years. In 2010, the Inuit Circumpolar Council, representing approximately 180,000 Inuit across Canada, Alaska, Greenland, and Russia, formally documented traditional ecological knowledge, including igloo construction, as part of climate change impact assessments. The documentation included a specific warning: changing snow crystal quality due to climate warming is already degrading the availability of construction-grade snow in traditional territories. The material that makes the igloo work wind-packed, crystal-interlocked, construction-grade snow requires specific temperature cycling and wind conditions to form. Those conditions are changing. The knowledge system for selecting and working that material, maintained in practice across generations, is under active threat of functional extinction within living generations. Not because the knowledge is being hidden, because the material it was built around is disappearing. The engineering survives. The material it requires may not. That is not a cultural observation. That is a materials science crisis. But the most revealing part of this story is still ahead: what this engineering means for buildings being designed right now. In 2024, Arctic engineers and sustainable architecture researchers are actively studying igloo thermodynamics as a direct model for passive house design. The properties drawing their attention: the catenary geometries, load distribution efficiency, the cold air trap entrance as a heat lock model, and snow's dual function as insulation and thermal mass. Modern building science uses the term thermal mass to describe materials that absorb heat during warm periods and release it during cool periods, smoothing interior temperature swings. Snow performs this function. The igloo wall absorbs heat from the interior, storing it in the crystalline matrix, and re-radiates it back as the interior cools. This buffering is why the Quillic, 60 to 100 watts, is sufficient to maintain habitable temperatures at -40 outside. The wall is not just blocking heat loss, it is banking it. Modern construction achieves thermal mass with poured concrete, rammed earth, or phase change materials, engineered products manufactured in factories. The igloo achieves equivalent thermal mass performance with no manufacturing, no transport, no energy input beyond the builder's labor. The comparison to fiberglass bat insulation bears one more number. Standard R13 fiberglass bat, the most common residential wall insulation in North America, requires a minimum 3.5-inch wall cavity to install. That means it requires a wood frame or steel frame structural wall before it can perform its insulation function at all. The igloo wall needs no secondary structure. It is simultaneously the structure and the insulation. In building science terminology, this is called a monolithic envelope, a single material system that provides both structural integrity and thermal performance. Monolithic envelope construction is considered advanced in modern sustainable architecture. Insulated concrete forms, structural insulated panels, and hempcrete blocks are current examples. The igloo is a monolithic envelope built from a renewable, locally sourced material requiring zero industrial processing. The U.S. Army Cold Regions Research and Engineering Laboratory has studied igloo construction because of these properties, not as a historical curiosity, but as an engineering reference for cold climate military shelter design. CRREL technical reports document the igloo's load-bearing capacity, R-value estimates, and construction efficiency as benchmarks for temporary structure design. The United States military, In other words, uses igloo engineering as a standard of comparison for cold weather shelter performance. There is one more structural detail that does not appear in most documentation of igloo engineering. The exterior snow surface of a completed igloo, exposed to cold air, undergoes sintering, a process in which ice crystals bond more tightly together at sub-freezing temperatures under light pressure. Over the first night after construction, the exterior wall surface hardens measurably. The structure becomes more rigid after it is built, not less. Modern building materials, wood, concrete, steel, require curing time or drying time before they reach design strength. The igloo reaches increasing structural integrity through the same cold that it was built to resist. The environment that is trying to kill the occupant is simultaneously improving the building. That is the paradox the engineering was designed around. Captain Lyon documented interior temperature differentials in 1824. Franz Boas documented construction sequences in 1897. The National Research Council confirmed the conductivity numbers in 1960. At each point, Western documentation arrived at something Inuit builders had already solved, and the documentation framed it as a discovery rather than a confirmation. The same thermal conductivity value that appeared in 1960 engineering literature was being applied in construction decisions on Arctic snowfields for roughly 4,000 years before that paper was written. The engineering predated the science by 4 millennia. The science caught up and called it a finding. This is the gap. This channel focuses on the space between what an engineering tradition achieves in practice and when Western science formally describes it. It is not a gap in capability. It is a gap in documentation framing. Igloo construction is not folklore. It is not a survival trick. It is not a cultural artifact preserved for heritage purposes. It is a complete applied physics solution to passive house thermal engineering in an extreme climate, executed without instruments, without manufactured materials, and without external energy input. If this engineering tradition is not documented on its own technical terms, in watts, R values, catenary geometry, thermal conductivity, it defaults to being treated as anthropological background, and the engineering disappears behind the story. We are trying to stop that from happening by using the same units of measurement the engineering deserves. The builder sits on the platform. The lamp burns. The walls hold at 30 centimeters thick. Outside, -40. Inside, 15 degrees, and rising. The structure doing all of that work was built in 2 hours from the snowfield it stands on, using a bone probe and a snow knife. Nothing was imported. Nothing was manufactured. Nothing was engineered after the fact. The engineering happened first in the selection of the material, in the geometry of the cut, in the angle of each block, in the shape of the entrance tunnel. That is what makes the thermal camera image so precise in what it reveals. The igloo is dark on infrared because the engineering worked as calculated. The modern house is glowing because the engineering, despite all its manufactured components, has not solved the same problem as cleanly. The builders who developed this system were not working from intuition or tradition alone. They were working from accumulated empirical observation, testing materials, refining geometry, calibrating ventilation across hundreds of generations. The documentation of that work in engineering units is not a translation, it is a recognition. Igloolik, Nunavut still stands. The Inuit Circumpolar Council still meets. Zacharias Kunuk's films are still in production. The builders are not historical figures. They are engineers working in a living tradition, some of whom are also currently advising climate scientists on snow crystal behavior in warming conditions. The engineering knowledge that built this structure is being applied right now to problems the modern world does not yet have instruments to solve. If you work in building science, thermal physics, or materials engineering, the igloo is a reference design, not a historical example. If you work in sustainable architecture, the monolithic snow envelope is a benchmark for what a zero-energy, zero-manufactured material building envelope can achieve. The numbers are in the research brief for this video. Links to CRREL technical reports, the National Research Council thermal conductivity studies, and the 2010 Inuit Circumpolar Council documentation are in the description. This channel covers engineering and materials science in Indigenous technical traditions documented in the units the engineering earned. 0.16 watts per meter Kelvin snow, selected by sound, shaped by hand, performing at modern fiberglass spec. 4,000 years before fiberglass existed, someone was already hitting that number, and the probe they used to find it fit in one hand. The U.S. Army Cold Regions Research and Engineering Laboratory has studied igloo construction specifically because of these properties, not as a historical curiosity, but as an engineering reference for cold climate military shelter design. CRREL technical reports document the igloo's load-bearing capacity, R-value estimates, and construction efficiency as benchmarks for temporary structure design. The United States military, in other words, uses igloo engineering as a standard of comparison for cold weather shelter performance. There is one more structural detail that does not appear in most documentation of igloo engineering: the exterior snow surface of a completed igloo, exposed to cold air, undergoes sintering, a process in which ice crystals bond more tightly together at sub-freezing temperatures under light pressure. It is a complete applied physics solution to passive house thermal engineering in an extreme climate, executed without instruments, without manufactured materials, and without external energy input. If this engineering tradition is not documented on its own technical terms, in watts, R-values, catenary geometry, thermal conductivity, it defaults to being treated as anthropological background, and the engineering disappears behind the story. We are trying to stop that from happening by using the same units of measurement the engineering deserves. The builder sits on the platform. The lamp burns. The walls hold at 30 centimeters thick. Outside, -40. Inside, 15 degrees and rising. The structure doing all of that work was built in 2 hours. From the snowfield it stands on, using a bone probe and a snow knife. Nothing was imported. Nothing was manufactured. Nothing was engineered after the fact. The engineering happened first, in the selection of the material, in the geometry of the cut, in the angle of each block, in the shape of the entrance tunnel. That is what makes the thermal camera image so precise in what it reveals. The igloo is dark on infrared because the engineering worked exactly as calculated. The modern house is glowing because the engineering, despite all its manufactured components, has not solved the same problem as cleanly. The Igloolik, Kavalik, and Kitikmeot builders who developed this system were not working from intuition or tradition alone. They were working from accumulated empirical observation, testing materials, refining geometry, calibrating ventilation, across hundreds of generations. The documentation of that work in engineering units is not a translation, it is a recognition. If you work in building science, thermal physics, or materials engineering, the igloo is a reference design, not a historical example. If you work in sustainable architecture, the monolithic snow envelope is a benchmark for what a zero-energy, zero-manufactured material building envelope can achieve. The numbers are in the research brief for this video, links to CRREL technical reports, the National Research Council, Thermal Conductivity Studies, and the 2010 Inuit Circumpolar Council documentation are in the description. This channel covers engineering and materials science in Indigenous technical traditions, documented in the units the engineering earned. Subscribe if precision matters to you more than the story you were already told. Leave a comment with the engineering problem you think this tradition solved that Western building science still hasn't caught up to. We have more of these. The data visualization and thermal modeling animations referenced in this script are timestamped in the description. Each frame is sourced to the specific study it represents. One final number, 0.16 watts per meter Kelvin, snow, selected by sound, shaped by hand, performing at modern fiberglass spec. 4,000 years before fiberglass existed, someone was already hitting that number. And the probe they used to find it fit in one hand